You're here because you want to learn the solubility equilibria with a University of Cambridge graduate. Let's begin. Solubility equilibria is a very short physical chemistry topic that is very similar and uses concepts from chemical equilibria, but in this case, it applies to sparingly soluble salts. So here I'll quickly summarize all the key pointers you need to take note when dealing with questions related to solubility equilibria. The first thing to take note of is to understand what is a saturated solution. A saturated solution is one which no more of the solute will dissolve. In other words, the maximum quantity of your solute is dissolved into your solution, of course at a very specified temperature. So what I like to imagine is you trying to dissolve your Milo powder into hot water, making your Milo drink in the morning, for example, and you will reach a point where you start to see these bits and pieces of solids of Milo powder that still is stuck inside your water and doesn't really dissolve. Then that's how you know that your solution is completely saturated with Milo powder. Next up, you have to understand what is the solubility of a compound. It is the amount of solute that can be dissolved in 1 dm cube of a given solvent to form a saturated solution at a given temperature. And last but not least, you also need to understand what Ksp is. Now, given K is obviously the equilibrium constant and it's also called the solubility product. So this is following this equation right over here. Now, this equation is derived from the balanced chemical equation, and you can just treat this like a normal chemical equilibria question where you are just using the products concentrations and to the powers of their molar coefficients. Just these. Do take note, Ksp is very similar to Kc or Kp. It only varies with temperature. It doesn't vary when concentrations change. Next up, we need to know the relationship between solubility and Ksp. Below is a table that details this relationship. What you want to do is form your Ksp equations first, as shown in this right column over here. And then you want to put in S as the solubility of the salt and sub it in for the concentrations that are used in the Ksp equation. So how do we do this? Well, if we look at the AB equation where the ratio of your ions are 1:1 and you let S be the solubility, that means that when S amount of compound is dissolved, you would get S amount of A plus and S amount of B minus. And therefore Ksp for this AB formula type would be S squared. Now what happens if you have A2B? Well, when you have A2B and S amount of solid has dissolved, then you would get 2S amount of A plus and S amount of B2 minus. And if you just sub these into the equation, you'll realize that Ksp equals to 4S cubed. Now you can do the same for the rest of the formula types, and you will see that the Ksp is actually related to S and can be easily calculated from one another. Next up, very similar to Ksp is actually ionic product. It's basically Ksp, but ionic product is used to calculate the ratio of concentrations, just not at equilibrium. So it's actually very good to predict if a solution has reached saturation, is oversaturated or is undersaturated. So if your IP is greater than your Ksp, that means the ratio of your ions in the solution is too high. It's higher than what is supposed to be at equilibrium. So what the equilibrium will try to do, or what the system will try to do, is get rid of ions in the form of precipitate. And that's what is happening. So your solution is actually saturated, but precipitate will form from the given state. If IP is equal to Ksp, then that means your solution is saturated and there will be no precipitate. In other words, the maximum amount of solute has completely dissolved within the solution. And lastly, if IP is less than Ksp, that means your solution is undersaturated. And if you put in more solid into the solvent, or put in more solute into the solvent, then the additional solute would continue to dissolve within the unsaturated solution. Next up is a question type known as selective precipitation of ions. So what happens here is you can actually separate the ions in an aqueous solution based on the precipitates that would be formed using a reagent that forms this precipitate with one or few of the other ions. So, for example, let's say I have Cl- and Br- inside a solution, and I can put in Ag+ as a reagent to precipitate out Cl- and Br-. Now, because the different precipitates that are formed have different KSPs, then you can look at the minimum concentrations of reagent that is needed to precipitate each of the ions. And obviously, the lowest concentration that is required would precipitate out first. So this is actually a good way to selectively precipitate different ions within a mixed solution. Now, another common question type that gets asked during exams is the common ion effect. This is where you have reduced solubility of a salt in a solution that already contains an ion that is common to the salt. Now, when you have an ion common to the salt within the solution, the ionic product will definitely increase and already exceed KSP, and therefore you would have precipitation, and because of this, the maximum amount of solute that can dissolve within the solution is lower, and therefore your solubility is lower. And do take note that still KSP does not change. Again, it only changes with temperature. So for example, in pure water, you have a AB solid that gives A+ and B-. And because they are 1:1, the equilibrium concentrations are S and S, which is the solubility of the salt. This is the normal solubility of the salt. So KSP equals to S squared. So if you are doing this not in pure water, but in 0.2 mole per dm cube Kb, that means there's an additional 0.2 mole per dm cube of B-. And this means that at the equilibrium concentration, there's always this 0.2 mole per dm cube of B- that you have to take into account. So you have to add that to the equilibrium concentration for B-. And just to distinguish, these are the new solubilities. And if you use these in the equation, your KSP would be S prime times S prime plus 0.2. And because you're using sparingly soluble salts, the solubility would be very, very low. And because of this, it's usually much less than 0.2. And therefore, we can equivalate S plus 0.2 as prime plus 0.2 to 0.2. And therefore, your new KSP is actually equals to 0.2 times S prime. We also know that KSP doesn't change. So if you look at the two KSPs, one is S squared and the other one is S prime times 0.2, you would see that because solubility is much lower than 0.2, the S prime is definitely much less than S. Well, not much less, but definitely lower than S. And therefore, the solubility of your salt will decrease when you have a common ion. So that's all for solubility equilibria. I would advise that you continue doing practices for solubility equilibria because the questions that come out of it are rather unique and a bit niche, and it would take a while to get used to the kind of questions and the calculations you need to do for these kind of questions. If you like this content, be sure to hit the subscribe button so that you can get more frequent updates from this channel. And if you want to enroll in my online class, be sure to hit the link below so that you can book a free call with me and I can run through your past papers and run through any doubts and clarifications you require and show you why my course is the best fit for you. I'll see you in the next lesson.